Everyone, respected teachers, faculty members, students, and my dear friends. I am Jyotiranjan Jena, and I would like to present my seminar topic on magnetic levitation.
ତଳକୁ ଦେଖ ତଳକୁ ଯିବାର ଅଛି। एस्केप था आपसे ये लास्ट में सीखो कंप्यूटर तो जाके तुम फिर सीखो ना
These are the contents. So first is what is magnetic levitation? How is magnetic levitation different from magnetic suspension? Uses of magnetic levitation, issue with magnetic levitation, Earnshaw's theorem, loophole in Earnshaw's theorem, magnet frame, electromagnetic suspension, electrodynamic suspension, application, advantages, and fusion projects in India. So, first of all, what is magnetic levitation? So, in order to move something in air, we have to apply some kind of force. So, levitation. In case of magnetic levitation, we use magnetic field to levitate any object. So, which is basically either ferromagnetic or paramagnetic in nature, and levitation.
Paramagnetic use ferromagnetic.
Magnetic not a diamagnetic.
Diamagnetic. फेरी ही पारे बट आरा वो डाया केमती हो
सुपर कंडक्टर केस जेतेबेले डायमैग्नेटिक फील्ड होय सेतेबेले माने लेविटेशन
डायमैग्नेटिक फील्ड
माने से डायमैग्नेटिक सुपर करना ये सुपर कंडक्टर
इट इज परफेक्टली डायमैग्नेटिक सी मैग्नेटिक फील्ड डायमैग्नेटिक रो किछि मैग्नेटिक फील्ड जैसे भारी हो डायमैग्नेटिक का कोई पिक्चर तो ठीक है चलो
magnetic levitation or magnetic suspension is a method by which an object is levitated or suspended with no support other than magnetic fields. Magnetic force is used to counteract the effect of gravitational force and other forces. Magnet can create frictionless, effective, and far efficient technology. So, basically, we are reducing all kind of contact forces when we are levitating an object. So, that's why it is very useful technology. So, how is magnetic levitation different from magnetic suspension? So, in magnetic levitation, we are applying repulsive forces from bottom of an object, whereas in suspension, we are applying from above it, right? So, we are suspending something in the air, and in levitation, we are applying forces given from the bottom. So, what are the uses of magnetic levitation? So, the first and most important uses in maglev frames. For high-speed ground transportation, maglev frames are designed to take advantage of magnetic levitation. And then second is contactless melting. Metals having high resistance can be levitated and melted in magnetic field, and then magnetic bearings for rotating machines to stabilize shaft without friction and contact. Magnetic bearings are used. Um, so, what are the most common issues while magnetically levitating an object? So, there is always an issue of stability, right? We have always tried to levitate an object like using a ring magnet and another set of magnets. So, we have always seen that it flips over immediately whenever we try to levitate it. So, there is also a theorem associated with it known as Earnshaw's theorem, which explicitly states that you cannot achieve stable levitation by using paramagnetic field or paramagnetic suspension. So, the primary issues involved in magnetic levitation are stability and lifting force. Lifting force should be sufficient enough to provide upward force to counteract gravitational force. The stability must be enough so that the system doesn't flip or slide or flip into a configuration. So, what is Earnshaw's theorem? Earnshaw's theorem states that a collection of point charge cannot be maintained in a stationary equilibrium configuration solely by electrostatic interaction. So, So it was first cited in reference to electrostatic interaction, but it is also applied for magnetic interaction. So, like, let's say there is a system of four charges. So let's just say this is plus q, and so it is placed on four corners of a square, and then we are bringing a point charge small q. So by Ohm's theorem, it says that this system cannot have a stable equilibrium. So if we move this charge q to, let's just say, a point p bar, so Ohm's theorem said that it cannot return to its equilibrium position. So let's just say, for instance, that this system is in equilibrium. So if we try to move this point as q to this point, so a restoring force should act on it. So for that restoring force, there should exist some kind of negative flux here, which is represented by a sphere. So for that, like now since the whole system is in equilibrium, so the forces that act on it, that is delta of F, should be equal to 0. Let's just say, let's just the equilibrium force is 0. So the equilibrium force acting on this charge q is 0. Now let's just say, uh, the force is represented by a scalar function, that is negative gradient of scalar function psi, right? So we know that the electric field is negative gradient of potential, right? So this system here, so if we like find the negative gradient of gradient of psi, and it should be equal to 0, because the force experienced here is 0, right? And then del square psi should be greater than should be less than 0, because this system is experiencing a negative flux, right? So therefore, the condition of stability is that the Laplacian of this function psi must be equal to 0. But we already know that that no charge should exist at this point, right? We are considering that the system has to be in stable equilibrium. That's why the negative flux is existing, right? So if there is no charge in the region, then we already know that del square v must be equal to 0, right? Because Laplacian potential is 0, because there is no charge existing at this point, right? So, but if we were to consider the system to be stable, then we have this condition. So they are obviously not satisfying. So the whole system is in an unstable equilibrium. So once we move the charge q out of its equilibrium position, it will never return back. So there is no restoring force acting on it. So this is what Earnshaw's theorem says, that we cannot obtain stable equilibrium with just static charges, right? This was first proven by British mathematician Samuel Earnshaw in 1842. It is usually cited in reference to magnetic field, but was first applied to electrostatic field. Earnshaw's theorem proved conclusively that it is not possible to levitate stably using static macroscopic paramagnetic field. The forces acting on any paramagnetic object in any combination of gravitational, electrostatic, and magnetostatic field will make the object position at best unstable along one of the axes, and it can be unstable along all axes. So loopholes in Earnshaw's theorem. So Earnshaw's theorem does not allow for a static configuration of permanent magnet to stably levitate another permanent magnet or material that are paramagnetic or paramagnetic against gravity. However, Earnshaw's theorem does not necessarily apply to moving paramagnets and diamagnetic material. These can thus seem to be exceptions, though in fact they are exploit of constraints of theorem. These are the three cases where we are basically exploiting the Earnshaw's theorem because even in this case, like the magnetic field is dynamic. This is not static. So first is spin stabilized magnetic levitation. So we have all seen certain objects called Levitron. So in that we are basically rotating a ferromagnetic substance with the help of a permanent magnet, right? So the stabilization is mostly due to what we call it as gyroscopic effect, right? So it is due to gyroscopic stability, and then there is servo stabilization. So what we do is so in case of servo stabilization, we just apply a feedback loop to a set of electromagnets. So whenever like let's just say that if this were to be a ferromagnetic object, so what we are doing is we are applying some kind of this is an electromagnet, so we are attaching it to a feedback system. So whenever it gets too far, the electromagnets are turned on, and whenever it gets too close, then the electromagnets are turned off. So there is a gap sensor between it. So that gap sensor determines whether when to turn on the electromagnet and when to turn off the electromagnet. So that is servo stabilization, and then there is diamagnetic levitation. So whenever some metals or ceramic substances are lowered below certain temperature, they exhibit the property of superconduction, right? So a superconducting material is perfectly diamagnetic, like the Surge stone. So this actually, like in diamagnetic substance, uh, it is actually magnetizing against the electric field, right? Against the magnetic field. So it is in the opposite sense. So therefore, it acts against Nelson's theorem. So that's what we utilize in electrodynamic suspension. We will go to that later. So now maglev frames. Maglev derived from magnetic levitation is a system of frame transportation that is levitated along a guideway by the use of magnetic forces. By levitating, maglev frames remove the rail-to-wheel contact present in conventional railways, eliminating rolling friction. So this is the most important advantage of any maglev technology. So we are levitating it, so therefore we are eliminating all kinds of contact forces, right? So compared to conventional railways, maglev trains can have severe advantages including higher top speed, superior acceleration and deceleration, lower maintenance cost, and lower noises at equivalent speed. However, maglev systems are expensive in build and cannot make use of existing infrastructure and have high energy usage at high speed. The maglev trains have set several speed records. The current speed record is 603 km per hour, which was set by SC Maglev in 2015. Despite over a century of research and development, there is only 6 operational maglev trains today, 3 in China, 2 in South Korea, and 1 in Japan. Different maglev systems achieve gravitation in different ways, which broadly falls into two categories: electromagnetic suspension and electrodynamic suspension. So, as we mentioned earlier, so electromagnetic suspension is based on servo stabilization, right? So in electromagnetic suspension system, the train levitates by attraction to a ferromagnetic, usually steel rail, while the electromagnets attached to the train are oriented towards the rail from below. The system is typically arranged on a series of C-shaped arms, like it is shown, like the shape is like C, and this is the electromagnet that we're using, which is known as support magnet, right? So this is actually the guide where the track, what we're calling. So this is made of ferromagnetic material, and this is attached to like feedback system. So it tells like whenever to switch on the electromagnet and switch off the electromagnet. So based on that, it achieves levitation. So whenever this electromagnet moves too far, it switches on the electromagnet. And whenever it moves too close, it turns off the electromagnet. So magnetic attraction varies inversely with square of the distance. So minor changes in distance between the magnets and rail produces uh, great varying forces. These changes in force are dynamically unstable. A slight variance from optimum position tends to grow, requiring sophisticated feedback system uh, to maintain a constant distance from the track. So we achieve a levitation of about 15 kilometers, that is right about 1 centimeter, by using this technology. So the major advantage of to suspended maglev system is that they work at all speed, unlike electrodynamic system which only works at minimum speed of 30 km per hour. This eliminates the need for a separate low speed suspension system and can simplify track layout. So now electrodynamic suspension. In electrodynamic suspension, both the guideway and the train exert a magnetic field, and the train is levitated by repulsive and attractive forces between the magnetic field. In some configurations, the train can be levitated only by repulsive forces. So the magnetic field is produced by superconducting magnets, as in SC maglev, or by an array of permanent magnets. The advantage of EDS magnet system is that they are dynamically stable. Changes in distance between the track and the magnets create strong forces to return the system to its original position. No active feedback control is needed. However, at slow speed, the current induced in these coils and the resultant magnetic flux is not large enough to levitate the train. For this reason, the train must have wheels or some other form of landing gears to support the train till it reaches the takeoff speed. Since a train may stop at any location due to equipment problems, for instance, the train track must be able to support both low and high speed operations. Um, so in electrodynamic system, we basically use superconductors. So it works by first step is by levitating, and then there is propulsion system, and then there is a lateral stability or guidance system, right? So in this case, the propulsion is based on the working of an uh, a linear motor. So linear motor is effectively an AC induction motor in which the stator and the rotor are cut from half and laid like a track. So the stator usually has copper windings, right? It has the three-phase power supply, which produces the effect of a linear magnetic field. So essentially, what happens is the rotor, which is also known as secondary, that glides over the stator, which is primary. So, in an instant, to say this is the general construction of a linear motor, right? So we can consider this part as the rotor, and this part is the stator, right? So this is the one that has the three-phase power supply. The combined effect is somehow in a linear direction. So it produces a magnetic field that propels the rotor in a linear way. So the rotor is basically any ferromagnetic substance. So what happens is it produces eddy current with respect to the varying magnetic field, and this eddy current has the direction is in such a way that it can effectively levitate over this thing, right? So this is how the propulsion system works for maglev trains, and now these are the common applications in aerospace engineering, spacecraft, rockets, nuclear engineering, military weapon engineering, civil engineering and building facility, biomedical engineering, chemical engineering, electrical engineering, architectural engineering, and automotive engineering. So, we discussed earlier, like there is the concept of magnetic bearing. So, in magnetic bearing, it is basically uh, the bearing parts are not in contact with anything, right? So it is basically levitating, so it eliminates all kinds of friction, right? Except for air friction. So the advantages, the foremost advantage of magnet train is the fact that it doesn't have moving parts as conventional trains do, and therefore the wear and tear of parts is minimal, and that reduces the maintenance cost by a significant extent. More importantly, there is no physical contact between train and track, so there is no rolling resistance. While air friction do exist, but that doesn't hinder the ability to clock in excess of 200 miles per hour. Absence also will also come as a boon, as they don't have to deal with deafening noise that comes with them. Maglevs are environmental friendly and they don't have internal combustion engines. So, like I stated, it works without any contact, and its propulsion is basically based on a linear motor. So these trains are weatherproof, which means snow or severe cold doesn't hamper their performance, right? So these are certain future projects in India. So these are only in working stages. None of them has been approved, but these are just plans for like future. Thank you.